We orbit a spark. Every morning we watch it rise. Every evening we watch it fade. We feel its warmth on our skin, watch it anchor our planets in their paths, and somewhere along the way we made a silent, collective decision. We decided our sun was powerful. We were wrong. Our sun, a nuclear furnace burning for nearly 5 billion years, commanding 8 planets across billions of miles, is, measured against the true scale of this universe, nothing more than a dim ember floating in an endless ocean of dark. And deep inside the Scutum Centaurus arm of the Milky Way, 20,000 light years from where you are sitting right now, something exists that makes even that ember look significant by comparison. A dying giant, a collapsing fire god. Its name is Stephenson 218, and it is the largest star ever discovered in the observable universe. Words like enormous fail here. Numbers alone won't do it either. The only way to truly feel the scale of this object is to place it in our world, to swap it into our solar system and watch what happens. So imagine our sun simply vanishes, and in its place Stephenson 218 appears. There is no warning, no dramatic buildup. The moment it materializes, its surface is already past Mercury, the innermost planet, a world of craters and extremes that has orbited for 4 billion years, ceases to exist instantly, absorbed without ceremony into the outermost layers of something incomparably larger. Venus follows, a dense, poisonous world of crushing atmospheric pressure, gone in a fraction of a millisecond. Then the wave reaches Earth. Every ocean, every mountain, every city and forest, every human being who has ever drawn breath, every civilization, every discovery, every moment of joy or grief in the entire recorded history of our species, consumed in silence. Not in a great explosion, not in a dramatic blaze, simply swallowed, folded into the interior of a star. We would not see it coming. There would be no last moment of awareness, just the sudden, absolute end of everything we have ever known. But Stephenson 218 keeps expanding. The boundary of dark crimson plasma surges outward. Mars disappears without a trace. The asteroid belt, millions of ancient rocky bodies drifting in their orbits for billions of years, vaporized completely. Then the expanding surface reaches Jupiter, the largest planet in our solar system, a gas giant so immense it contains more than 1,000 Earths inside its swirling, violent storms, a world that nearly became a star itself. It doesn't matter. Jupiter is swept beneath the rolling surface and incinerated without resistance, gone, as quietly and completely as everything before it. The star continues to expand past Saturn, and if a human being could somehow stand on one of Saturn's frozen moons in that moment, looking inward, there would be no black sky, no stars, no darkness at all. The entire universe above them would be replaced by a curved, endless wall of glowing crimson plasma, stretching from every horizon, pressing down like a ceiling of fire. 10 billion of our suns could fit inside the volume of this single star. But even that comparison doesn't fully communicate what we're dealing with. So let's use something more fundamental. Let's use light. Light is the universe's absolute speed limit. Nothing travels faster. It moves at nearly 300,000 kilometers per second, fast enough to circle the entire Earth 7 times before your heart completes a single beat. A beam of light fired across the diameter of our sun finishes that journey in roughly 14 seconds. Fire that same beam across the diameter of Stephenson 218. It doesn't finish in seconds. It doesn't finish in minutes. That beam of light, traveling at the fastest speed reality permits, takes nearly 9 hours to complete a single pass from one side of this star to the other. 9 hours. At the speed of light. If you flew a commercial aircraft at cruising speed along its equator, the journey around the star would take approximately 500 years of continuous flight. This is not metaphor. This is measurement. And yet, for all its incomprehensible scale, Stephenson 218 is not stable. It is a star in crisis, a titan losing a war against its own existence. Its outer layers are so extraordinarily distant from its core that the gravitational force holding them in place has become dangerously weak. Every second, the star sheds millions of tons of its own material into the surrounding darkness, bleeding into a vast shroud of radioactive dust and stellar wind that extends billions of kilometers into the void. Its surface is not the smooth, glowing sphere we might imagine. It is a violently unstable ocean, enormous convection currents rising from deep within, colossal bubbles of superheated plasma surging upward from the core and exploding into space with unimaginable force. A single one of those surface eruptions is larger than our entire solar system. One eruption, bigger than everything humanity has ever known, mapped, or explored. But this violence has a cost. Stephenson 218 is burning through its nuclear fuel at a rate that cannot be sustained. It has to. The crushing gravitational weight of its own outer layers demands a constant, enormous outward pressure just to keep the star from collapsing inward on itself. It is burning too fast, living too hard, and it is running out of time. At some point, perhaps soon by cosmic standards, the fuel in its core will be exhausted. The outward pressure of nuclear fusion will stop, and gravity, the patient, silent, unconquered force that shapes all things, will finally collect what it is owed. The outer layers of the star will fall inward at a terrifying fraction of the speed of light. All of that mass, all of that scale that swallowed our solar system whole, collapsing toward a single point in less than a second. The universe itself will shudder. The resulting explosion, a hypernova, will briefly outshine the entire Milky Way galaxy. A pulse of gamma radiation will travel outward across the cosmos at the speed of light, stripping the atmospheres from planets light years away, sterilizing any world unlucky enough to lie in its path. The star's body will be torn apart and scattered, an expanding cloud of radioactive matter drifting outward into the dark. And at the exact point where the largest star ever discovered once stood, there will be a tear in the fabric of space itself, a singularity, a point of infinite density, a black hole, born from the collapse of a fallen giant. We are 20,000 light years away. We are safe. The death of Stephenson 2-18 will not reach us. Its radiation will not touch this world. We will likely never even witness it happen. The light from that explosion, traveling across 20,000 light years of space, may not arrive here for longer than human civilization has existed. But knowing it is out there, right now, burning and bleeding and slowly losing its battle against gravity, changes how the darkness feels. The night sky is not a calm, peaceful backdrop. It is a wilderness, ancient, vast, and indifferent. A graveyard of objects so large they collapse the meaning of every word we use to describe size. Out there, beyond the reach of everything familiar, there are scales that the human mind was simply never built to hold. We are small, extraordinarily, almost beautifully small. But we looked up. We pointed our instruments at the dark. We found this thing, this impossible, dying colossus 20,000 light years away, and we measured it. We understood it. In a universe of unimaginable scale, the fact that something as small and brief as a human being can look into that darkness and comprehend what lies there, that is not nothing. That might be everything. The giants will fall. The stars will go dark. But right now, in this moment, we are here, curious, awake, and looking up. Don't stop looking up.